Well, welcome everybody. This is Mr. Bergman.
Greetings.
And that is Mr. Sams.
Greetings.
Hey, we were just talking about our childhood. And Mr. Sams and I were relating stories from when we were your age.
High school hood.
A high school hood? I didn't go to a hood of a high school.
No, I didn't either.
I was actually in a privileged high school, I must say. It was, a bunch of rich kids. Although we weren't rich. I don't know how we got there. We were military, so I don't know. Somehow we fit in a little bit. I don't know. But I tell you a story. Mr. Sams and I were telling a story, and I tell you the story, when I was in high school. I think I was a sophomore. I know I was a sophomore in high school. I was actually just telling my son this the other day. And because he's a sophomore in high school right now. And I had a buddy, and he was a single child, and so he took us. He would invite friends of his on vacation, and so that's a car.
What is that?
It's his car.
Oh, okay.
And his parents would take us camping. You don't like? Am I drawing?
Oh, it's a trailer. I see. I had no idea where you're going with that.
They had a trailer, and they took us to the lake because they had a boat. Actually, they had a trailer and a boat. They had two cars, like Mom drove one and the other. So they took a trailer. They didn't do the two things. And they'd go water skiing all the time. And so we were going water skiing a vacation because this kid was an only child and he had no friends except me. So so long story short, I got on my bicycle. We were at the campground. I don't know if you've ever been camping, but they have like campgrounds. So Mr. Bergman is on his bicycle. That's me on my bicycle. Okay, and I'm driving around the campground. You're laughing at my diagrams. And there was this pretty girl. And my eyes focused on the pretty girl. It's really not a good idea, Mr. Sams, to focus on something else when you are riding your bicycle.
No, you always want to look where you want to go.
And see, I was looking at her because she was pretty.
Right.
I was 16 or whatever I was, 15, 16 years old. Long story short, I looked down and I said, uh-oh, we have problems. Because there was this big rock because I had steered off the road a little bit. And then Mr. Bergman's bike stopped. It's actually quite a physics moment here.
Yeah.
What does it say? An object in motion
will stay
in motion. You see, the bike stops. Mr. Bergman flies over the top. He actually lands on his face. Right on his jaw. And I broke my jaw. Snap, crackle, pop. And then, of course, the parents of my friend Jim was his name. They had to drive me home like 150 miles from the lake back to the town that we lived in. Yeah, it hurt a lot. In fact, the funny thing about this story, they're driving me back, and they'd called ahead. This is before cell phones. They called my family and said, we're going to meet you at the hospital. They didn't know where the hospital was.
Oh.
And I did. And so I have to communicate with a broken jaw to the parents in the front. And they didn't have paper and pencil. And so I'm signing with my hands, and somehow I communicated with them.
Where the hospital
was. It was on Hayward Street or something. Or I don't know. And I had to somehow, I think I was using rudimentary sign language. Is that an H? H? G? Yes, it's an H. All right, hey, H. All right, H. All right, no, it's the next letter. We were playing like, what do you call that? Charades. Mercy. It was an interesting day. So next time, Mr. Sam's going to tell you about how he hurt himself.
I am the only person in my high school's history to have a speech and debate injury.
Injury.
Yes.
So he had injury. So we will have to hear this story. I think it will be interesting. All right. 3-minute story there. Okay, if you needed to fast forward to that, hopefully you enjoyed that. Okay, acid-base indicators. Okay, today we're going to learn about acid-base indicators.
Yeah.
We've known that there's two ways to indicate that you're at the end point of a reaction, right?
Yep.
It's the steep portion of the graph or whatever. And the second was the indicator. Okay. But how do indicators actually work? So there's some chemistry behind indicators. Yeah. All right. Actually, I guess I've already done this. How do you know if an ending point is reached? Colorimetrically, that's when you see a color change, which I just sort of alluded to.
Hence the name.
Colorimetric. And the pH meter is the center of the steep portion of the graph. It could look like that, or it could be the opposite deal. Okay, so we've sort of already learned that. So I don't think that's really that important. But how do you pick an indicator? Which indicator do you actually use?
I like the one that makes the nicest color.
Oh yes, the pretty one. You like the pretty one. It makes it very pretty.
Yeah.
That's not a really good idea, Mr.
Yeah, it's not a very good way of
picking. It's not going to work. Okay. Actually, the first thing you would do is actually do the indicator graph thing, the pH graph. So you would do this graph, and then you would find the pH at which it changed. Now remember, we learned that they're always not 7,
right,
unless it's a strong acid, strong base. This example that I've drawn is probably a weak acid versus a strong base, and the pH is greater than 7. But we also learned in our last podcast that if I had a weaker acid, it actually might do something like this, and then the pH would be even much greater than 7. So the first example I just did a minute ago, well, this might be a pH of, say, 8.5, and this one would be a pH of 10.5. So which indicator do I use?
Now we got to find one that changes in that range.
So then you have to use a chart. So if you look at the chart in your book,
yeah,
it looks something, or in your handout, I should
yeah,
say, but it looks something. It looks just like this. You're probably, you don't have the color version. You have the black and white version.
Yep.
So hopefully we have the colors written out. Ours is in color because it's pretty. Okay, but you get the idea. So if I knew something would change at a pH, if I did the pH graph, so let's go back to the one I had here. This one, let's say, we figured out would change at 8.5. So it changed to 8.5. Which indicator would I use?
Thymol blue, second transition, up at the top or down there. Phenolphthalein would be a good one.
You wouldn't use one that has second transition.
Yeah,
because that's actually,
not good. Yeah.
You usually want to do one that has one transition. There are
Yeah.
times that you would. That would be fine. Actually, the interesting thing about this is if it's got a really steep curve, frankly, your choices. If, let's say, this pH right here is 4.5, and this one is 10.5, you're looking for something that will clearly change
in that range.
anything in that range, and so we have lots of choices that we could make here. Frankly, I said 4.5. I think I would choose brome crescel purple.
Oh, that's a pretty one too. See, it fits my description as well.
All the way up to maybe I might use
maybe phenolphthalein.
I would use phenolphthalein. Yeah. Phenolphthalein is a great one. That's the one you're very familiar with. Of course, it's colorless in an acid, and you're looking for something that's a strong color change. This isn't a bad one. The crescel red goes from yellow to purple. That's probably something that's pretty noticeable.
The easy ones to see are going from colorless to something colored.
Yes.
Those are the easiest to see.
Now this one, red to yellow, is sometimes that transition is hard to see. So for the natural red,
like, is it still red? Is it orange? Is it yellow orange? Yeah, those are kind of.
So those are some interesting things. So or my second example, which I think I gave you examples. Did I not? Oh, I did.
Yeah.
I should probably use this. Well, we'll use this one. If I have 10.5 as the color change, probably I'm going to use this thymol. Phthalene probably or something.
Yeah.
You get the idea, I think. Let's take a look at a couple of examples here. So if I have the graph here, which indicator would you pick? Would you choose phenolphthalein or methyl orange?
Phenolphthalein.
That's the reason you would, of course, is because methyl orange changes after it's reached the equivalence point. So methyl orange would be a bad choice.
Yep.
What about this particular one right here?
Yeah, that's still on, even though it doesn't touch the equivalence point, it's still on that really steep part of the graph, and so methyl orange is going to be just fine.
So in this case, you choose methyl orange. Yeah, it's at the bottom end of the graph, but it's still going to work just fine. And one last one. What about this one right here?
Well, it depends on which equivalence point you're looking
Yeah, you
for.
see, you're looking at, this is a diprotic base, a alkaline base, whatever it's called, because it's got two different steep points. So if you're looking for the first equivalence point, you would take phenolphthalein. If you're looking for the second equivalence point, you'd use methyl orange.
Yeah.
Okay, now how do these things work? How does an indicator actually work? Do you know this? All indicators
are weak acids or bases.
Actually, they're all weak acids, I think, aren't they? No, some are bases. Yeah, you're right. What happens is, if I have a weak acid, we'll call them HIN, where IN is the
indicator.
The indicator ion, if you will. It breaks apart into hydrogens and the IN negative. Now, this is assuming that it's a monoprotic acid.
Right.
It could be diprotic acid, too.
A lot of them are, actually.
And a lot of them are. And if, let's say, that the HIN is blue and the IN negative is green, then what would happen is, of course, is as you add base, this forms water.
Yep. And then we have Le Chatelier's principle kicking in.
Which we haven't really talked about yet with these guys. Yes, we have.
Yeah.
Le Chatelier's principle kicks in. You're right. And so that takes away hydrogen, which drives this reaction back to the left, and it's going to turn
to the right.
I said that wrong, didn't I? Yes, it'll drive this reaction to the right, and it will make this solution blue. Green. I'm really good at this. Okay, I'm not getting this figured out. Okay, and conversely, if I were to add hydrogen to this, All right. If I were to add, this is getting confusing. So if I've got HIN turns into H positive plus IN negative, and I forget my color scheme I made up here. Blue and green. This is blue, and this is green. So if you were to add am I ADD?
I don't know.
H positive, it would drive this
Probably
reaction
just hungry.
to the left, and it would, it's hungry. That would turn this blue.
Right.
And so that happens at a particular pH. And so it's just, I think the key thing to understand is that they are weak acids and bases, and they have their partners, and each partner has a color. Sometimes one of the colors is colorless, or whatever, and many of them can be, say, sort of diprotic. All right, let's do an example here. The equivalence point of a titration is 4.3. Which one do you pick? Now, notice here we have a list of their Kas. So on the previous ones, we had like this cool picture graph thing, but I don't have the picture graph, but I'll bet you can figure out this one. It's very uber simple. Basically, where this is 4.3, what you're looking for is the one where the pKa is closest to, in this case, 4.3. Now, I'm not going to get a calculator out and do each of these.
Yes, that's going to be a
because let me just do it in my head. If this is 10 to the minus 11th, the pKa is going to be about
a little less than 11.
Like 11. This one's going to be like a 9. This one will be like 8. Actually, it's going to be a little bit less. So this is 9. This is probably 8.7 or 5, 4. Who knows? Something like that. But it's a bit less. This will be about like 6. This will be about like 5, and this will be like 2. So if it's 4.3, if we're looking for something that's in the 4 range, remember it's always a little bit less. So endocrine black is our answer in this particular case. They're not terribly difficult. You just take the negative log of this, or you just look at the exponent. The one closest is the wiener. Okay? All right, hey.
All right, something new.
New
We're kind
topic.
of shifting gears.
New topic.
Not acids and bases anymore.
We are done with acids and bases?
We are.
Completely done?
Yeah.
If you haven't figured it out by now, ask lots of questions. Because you probably will need them.
Yep. Now, this is still an equilibrium system.
Now, let's actually talk equilibriums right now for a second. There are different varieties of equilibrium we've been talking about so far. Before we talk about this,
KP.
we've learned about KP. What's the P stand for?
Pressure.
Pressure. Okay, and we found KC.
That's just concentration.
Concentration. By the way, also sometimes just K.
Yep.
We learned about KAs. That would be acids, right? KBs, that would be bases. KW, that's really special, that K of water. And now we have any more?
KS, no, that's it. Now it's just KSB.
We have one more K. Now it's capital K. Small k, remember, is a rate constant. Big K is equilibrium constants. We have one more K. It is called the solubility equilibrium.
Yes.
So it is the study. Actually, the SP, by the way, stands for solubility.
Person.
Bility.
B-I-L-I-T-Y.
Product. What's product mean?
The thing that's produced.
Well, not in this case.
Oh, multiplication.
In this case, the product reference is the multiplication. It's a mathematical term, times. Okay. Now, the KSP is kind of a weird thing. Is the study of insoluble. It's the study of the solubilities of insoluble ionic compounds.
That sounds a little contradictory to me,
That
Mr.
does
Brooks.
sound contradictory. We're going to study the solubility of things that are insoluble.
Right.
What? That doesn't make no sense.
No, because nothing's actually insoluble.
Yeah.
No such thing.
Now, when we say solubility, remember, we're talking about naclnosos. Things that we've memorized are soluble.
Right.
All sodium compounds are soluble. All chlorides are soluble. All nitrates, all sulfates with exceptions, and da-da-da-da. And then
everything else is insoluble.
Not soluble. But guess what? We've sort of...
We lied.
Lied to you, yes.
We're horrible people.
Well, because everything is actually, to some degree, soluble.
Right. So all those things that you learned as insoluble, keep them in the back of your brain that they're still going to form precipitates if they form products. But they still dissolve a little bit.
So everything is at least slightly soluble.
And some things it's like ever so slightly, and infinitesimally slightly, but it's still slightly.
And this is the study of that slightliness.
Yeah.
Is that a good
Slightliness.
word?
I like it.
Slightliness. There you go.
Nice.
So let's take some insoluble compounds.
All right.
Now, calcium fluoride is actually a naclnoso because you have a fluoride. you would think that it was soluble. This is sort of an exception to the exceptions.
It is a weird one.
But for all intents and purposes, we're just going to dissociate that. It's a solid.
Mm-hmm.
So if you took calcium fluoride, you dropped it in water, it would settle to the bottom.
Yes.
And it would make, but some of it...
A tiny little bit makes Ca plus 2, or 2 plus.
2 plus.
And 2 F minuses.
Fluoride. So let's kind of draw this pictorially. I think in a beaker. You don't like my beakers.
The drum.
All right.
Dum, da, 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 dum,
We have a liquid.
50-gallon drum.
A 50-gallon drum. And if you were to take calcium fluoride in just powdered from like a container and drop it into water, the vast majority of the calcium fluoride would be a solid that would settle at the bottom. But a very small amount of them would break apart into calciums and fluorides.
And we can figure out how much of it does.
And we can figure out how much of it does. Okay, and it would go with this equation. So we can actually write what's called the solubility product expression, which is called a KSP.
Yeah.
Which is just the K expression. K expressions, as you recall, is the products over the reactants.
Right.
So that would be equal to the calcium times the fluoride.
Squared.
And you have to square it because of the 2 here. And we've done this before. Over
nothing.
Over nothing? What do you mean nothing? Products over reactants.
Right.
But what's up with that? I thought it was products over reactants.
It is.
Why couldn't I put the key?
Because that's a solid. We are only concerned with things that are aqueous in the system.
You have to actually have, it's not really that it's solid.
No,
it's that
it's just different.
Homogeneous equilibrium. You must have the same state of matter. And since this is aqueous, I didn't write that in there, and this is aqueous. When you have charges, it's implied that it's aqueous. These solids get ignored. So you actually, these math are actually easier because you don't have a substance on the bottom. This second one would have the same deal, magnesium phosphate. It would break into 3 magnesiums with the 2 positive charge plus the 2 phosphates. And then the KSP expression would be equal to the magnesium, Mg2 positive, and what would do? What's that, Mr.
Cubed.
Sims? Cubed because of the 3 right here. And then the phosphate, and you would square that. And then barium sulfate, the classic one everyone uses, Ba positive 2. Now remember, all sulfates are soluble except for barium and other varieties, and this is one of those ones. It's insoluble, so it breaks apart, and we can say the KSP is equal to the concentration of the barium, 2 positive, times the sulfate, 2 negative. And they're both to the first power because, of course, this is a 1-to-1 ratio.
Yep.
Now, there are tables of KSPs. You have one printed up in your table. It's also in the back of your textbook.
A25 if you have Zumdahl 6th edition.
Now, I want you to take a look at all those numbers, Mr. Sims. What do you notice about all those numbers?
They're tiny.
10 to the minus 6, 10 to the minus 13th, 10 to the minus 23rd. Have mercy. And if you go down even further, 10 to the minus 49th for silver sulfide, 10 to the minus 88 for iron sulfide.
Nice.
That is a tiny number.
Yeah.
I think I heard somewhere that there are 10 to the 82nd power atoms in the universe.
Wow.
So this on the other end of the scale is at the same magnitude of that. Yeah.
That's nuts.
Yeah, so that's a tiny, uber tiny number. All right, we're going to use some of these uber tiny numbers next. All right, now when we talk about the solubility, we usually measure the solubility in something called molarity.
Yes.
And we all know what molarity is, moles per liter.
Moles per liter.
So we want to find the solubility of this copper-1 bromide.
Yes.
So what I write is I need to write the formula of copper-1 bromide.
Yes.
Now that means Cu plus 1 and Br minus.
Yes.
Such as CuBr.
CuBr.
CuBr. Goober. Is that like goober?
Kind of.
Pile or something?
Yeah.
Right. Makes Cu positive 1.
I think you just dated yourself.
Plus Br negative. It's Gomer pile.
Gomer pile.
It's Gomer, not goober.
It is. And our students don't have a clue who that is. I only sort of know that because I used to watch it on Nick at Night.
I'm old. So, folks, yeah, it's my own fault for being old. Okay. Now, we know that the solubility of copper-1 bromide is 2.0. So actually, let's just write the KSP. It's asking for what's the KSP.
Right.
Well, the KSP is equal to the concentration of the copper, positive 1, times the concentration of the bromide. And the solubility is how much breaks up.
Yes.
Now, this is a tiny number.
Right.
That means that there will be 2.0 times 10 to the minus 4th for the copper, and 2.0 times 10 to the minus 4th for the bromide.
Right.
So actually, what this is giving you is the values that you're going to place into here. So you can say 2.0 times 10 to the minus 4th times 2.0 times 10 to the minus 4th. So essentially you're going to square that number.
Yep.
You get 4, I could do this, times times 10 to the minus 8th, right?
Yep.
Is equal to the value of the KSP. Now, what would be the units on KSP?
It could be mole squared per liter squared, but we really don't care about units on KSP because they're going to be different for every substance.
I'm not sure we've said this, but in all Ks, the units don't matter.
Nope.
In the equilibrium K,
in kinetics,
K,
they often do.
It does. So you just...
Doesn't matter.
Yeah.
Ignore them.
Okay.
You have our permission to not write units.
Now, what if I do this one? What is the molar solubility of silver sulfide?
Well, that's just kind of working in reverse.
Yeah, so if I've got silver sulfide, now Ag is positive, and S is -2, so that's going to be Ag2S, right?
Yes.
And that's going to break apart into 2 silvers, and then S2 minus.
Yeah.
So when this breaks apart, it's almost like a BCA table, but not exactly.
Yeah.
I like to call it the 2, this is going to, because of this 2, going to break down to 2S. As opposed to an X. I think an S for solubility.
Okay, I can live with that.
And this will be an S. And we know that the KSP is equal to the concentration of the silver positive squared times the S -2. But this is 2S and this is S.
Yeah.
And when the KSP value, we can go back and find that in our table.
It's 1.6 times 10 to the -49.
Oh, this is one of our small ones. Is it on here? There it is.
That says 1.0. My book says 1.6. Interesting. I'm going to go with the Zumdahl textbook.
1.6 it is. All right. All right, now I go back to my place. So I can say 1.6 times 10 to the -49th would be equal to 2S. I'm going to substitute this 2S in for silver, and I'm going to square it, times it by the S. Now, a lot of students will make a mistake here.
Yes.
What is 2S squared times S? Most students will say, well, it's 2S squared. And that would be wrong, because this 2 right here is squared. So it's 2 squared. So 2 squared is 4. So this becomes 4S cubed. Yes. So now I'm going to solve for S. You can put it in your solver, although this is almost not even a solver.
I'm not going to use solver.
I divide both sides by 4.
Times 10 to the -49.
And then I got to take the cubed root. Now, what I would do is actually take it to the power of 1 divided by 3. So whatever he gets when you divide by 4, you take it to the 1/3 power. That is the same thing as the cubed root, and you get the molar solubility to be
3.4 times 10 to the -17. I don't even know how to do cubed root on this calculator.
There is a way, and I'd have to sit and think about how to do it.
Yeah.
All right, so that means, now what does that actually mean? That means if I had a bucket, of silver sulfide, and I put some silver sulfide on the bottom, it would be a powder. I could put, and it wouldn't matter how much I put. I could put 100 grams or 10 grams or 1 gram. It would settle as the bottom. It would be a powder at the bottom. I don't know what color it is. And then you'd find some silvers
kind of black.
and some sulfides.
When silver tarnishes, that's silver sulfide.
Oh, that's right. Yeah, I think I did know that.
Yeah.
Okay, so you would find the silver black.
Perfect.
Okay. Then you would find the silver sulfide, but the concentration, the solubility, the concentration of this would be that number we just calculated, which was
3.4.
3.4 times 10 to the -17th molar. Now, most molarities we work with are like 0.1, 1. This is 10 to the -17th molar. This is it. So, did it dissociate?
Yeah.
Just an itsy bitsy small amount. But this amount, now you say, why do we study this? Well, there's actually some really cool applications to this, which we will learn about probably in our next podcast. All right, one more. What about bismuth 3 sulfide? So bismuth has a charge of +3, sulfide -2. So that's going to be Bi2S3. And that's going to break apart into 2 bismuths with a charge of +3 plus 3 sulfides. Now, this is going to break apart into 2S and 3S. Okay? And our KSP expression would be equal to the bismuth squared
because of the coefficient
times the sulfide cubed.
Because of its coefficient.
So we can now, the value of the KSP is
given in here.
1.1 times 10 to the -73rd would be equal to 2S squared times 3S cubed. Now, a lot of students ask me this question. I hear this question often asked them. Mr. Bergman, you have this 2S, and then you're also squaring it. You're dealing with that 2, or in this case, the 3 twice.
Yep.
And you know what? They're exactly correct. Why you do that? Because you do.
It's just the way the math works.
It's the way the math works. I don't want to, there is a deeper answer. Deeply read your textbook, and I don't even think they even answer that question. But
not very well.
Or at least not very well. So now, I can see if I can do this in my head. 2 squared would be 4. So this would be 4S squared.
Yep.
Now 3 cubed, 3 times 3 is 9, and then 9 times 3 is 27. So this will be times 27, that's a 7, s cubed. So 20, that's 108 maybe, is that right? 27 times 4?
27 times 4 is 108, yeah.
108 s to the 5th. So now I'm going to say, I'm going to get a new screen here, I'm out of space. 1.0 times 10 to the minus 73rd is equal to 108 s to the 5th. Divide both sides by 108. Those cancel. What do you get when you divide those, Mr. Sam?
1.02 times 10 to the negative 75.
And that is equal to s to the 5th. So if you take this number, so you take 1.02 times 10 to the negative 75.
Take the 5th root of it, or take it to the 1/5 power.
Parentheses 1 over 5,
yep.
Parentheses, equals, or enter, and you get
1.00 times 10 to the negative 15.
Makes it a lot more smaller. Actually, interesting thing about this problem, this one had a very, very, very small KSP, but the molar solubility of this one was 10 to the minus 15th. The previous problem was, actually let's go to this screen, was 10 to the minus 17th. This was actually less soluble, the silver sulfide, than was the bismuth one. It has to do with the fact that this is this 5th power and the mathematics of it. And so again, what would this look like if I were to draw a beaker of the bismuth sulfide? Okay, you would find the bismuth sulfide down here, the solid Bi2S3, and then you would find bismuth ions and sulfide ions up here, and they would be, the concentration would be, what did we say, 10 to the minus 15th molar. Still very, very small, but some of these break apart and dissolve, but just in very, very small amount.
2.
Yeah, I mean, 10 to the minus 15th, 10 to the 9th is a billion, 10 to the 12th is a trillion.
So whatever's after a trillion,
quadrillion
parts per.
So 1 in every quadrillion molecule breaks up.
Yeah.
And you say, why do we care? We'll show you later. That'll be on the next podcast.
Yep.
And what do you get to hear about on the next podcast?
How Mr. Sam's speech and debate injury.
The speech and debate injury. Yes, indeed. We will hear interesting stories about Mr. Sam's. I look forward, because I do not know this story. I want to know. So we will see you later, possibly in class, or if you're watching this via the internet and you're one of our internet kiddos, maybe you'll never meet us. Oh, well. Have a good day. Bye.
Bye-bye.